Welcome to the Mathematics of Thinking. In this playlist, we'll be diving into famous variety of algorithms. We'll be breaking them down into visuals and in order to understand how they empower every tool we use every single day as a data engineer. So yeah, let's get started. So far in this series we have covered graph algorithms, topological sort in Dijkstra, and probability model with Markov chains. Today we go somewhere completely different, and I promise this one is the most visually satisfying video in the series. Today, Monte Carlo simulation. I'm going to show you how you can estimate pi, the mathematical constant 3.14, 15, etc. by throwing random darts at the square. No calculus, no formulas, just randomness and counting. And then I will show you why this exact technique is used in a nuclear physics, financial risk management, and the AI system that beats the world champion at Go. Imagine yourself again trapped in this situation. Some problems are simply too complex for exact mathematics. Integrals with no closed form solution, systems with hundreds of variables interacting simultaneously, risk calculations that need to count for millions of possible scenarios. Exact math breaks down, numerical methods become too expensive. What do? Here is the insight. If you cannot solve the problem exactly, sample from it randomly. If you draw samples from the right distribution, the average of those samples converges to the true answer. That is the law of large numbers. It is one of the most powerful ideas in all of mathematics, and the precision scales with the number of samples through 100 random darts. Rough estimate through 1 million, extraordinary precision, no calculus required, just randomness and counting. This technique is called Monte Carlo simulation. It was named after the casino in Monaco because of its reliance on randomness, and it was invented in 1946 at Los Alamos for simulating neutron diffusion in nuclear fission. Today, it powers everything from hedge funds to game AI. The Monte Carlo method has 3 steps, always 3 steps. Step 1, sample generates a large number of random inputs from a defined domain. The more samples, the better the approximation. Step 2, evaluate for each random sample, run your experiment, check whether it satisfies the condition, compute a value from it. Each sample is an independent trial. Step 3, aggregate, count the successes or average the value. By the law of the large number, these aggregates will converge to the true expected value. Look at the bottom panel. Those are real convergence numbers for pi estimation with 100 sample 3.16 off by 0.6%. With 10,000 we get 3.14 off by 0.06%. With 1 million we get 3.1416 off by just 0.0002%. The more samples, the closer you get, guaranteed mathematically. The pi estimation, the math. So let me show you exactly why this works geometrically. This is the cleanest derivation I know. Draw a unit square, side length is 2, so x goes from -1 to +1, y goes from -1 to +1, area is 4. Now inscribe a circle of radius 1 inside that square. Area of the circle equals to pi times r squared equals pi times 1 equals pi. Now imagine throwing darts completely randomly at the square. Each dart lands at a uniformly random position, no bias. A dart lands inside the circle if and only if x squared plus y squared is less than or equal to 1. This is the equation of a unit circle. Here is the key. The probability that a random dart lands inside the circle equals the ratio of the two areas, so pi divided by 4. So pi over 4 equals inside over total, therefore pi approximately equals 4 times inside over the total. So that's it. That's the whole algorithm. Throw darts, count how many lands inside the circle, multiply by 4. That is your estimate of pi. Look at the right panel. That is exactly what it looks like visually. Tail dots inside the circle, coral dots outside. The more the dots you throw, the clearer the ratio becomes. Let me trace through this with actual numbers. So the setup is we define our square from -1 to +1 on both axes, initialize inside and total to 0. Dart 1 x equals 0.62, y equals to 0.38. We compute we compute the x with the y, squared y squared equals to 0.529, that is less than 1. So this dart lands inside the circle, inside becomes 1, total becomes 1. Pi estimate 4 times 1 over 1 equals 4.0. Very rough, but we only have one data point. So dart 2 x equals minus 0.91, y equals 0.72, 0.829 plus 0.518 equals to 1.347, greater than 1. Outside the circle, inside stays 1, total becomes 2. Pi estimate drops to 2.0, still converging. Dart 5, after 5 darts, 4 are inside. Pi estimate 3.20, getting closer. Dart 10, 8 of 10 inside. Pi estimate to 3.220, again no jump to 1 million darts, approximately 785, 398 lands inside the circle. Pi estimate 4 times, over and over until we get to 3.14159. that is 99% accurate. So from random darts to 5 decimal places of pi, no integral, no formula, just counting. Let me show you the convergence data clearly. So at n equals 100, estimate 3.16, error 0.57%. At n equals 100, estimate 3.148, error 0.21%. At n equals 10,000, estimate 3.1404, error 0.04%. At n equals 100,000, estimates 3.1418, error 0.008%, and until we downgrade the error percentage. So look at the bar chart on the right. The error bars decreases visually as sampling or samples increase. At n equals 100, the bar is huge, large uncertainty. By n equals 10 million, it's almost invisible. Now the critical insight at the bottom, error shrinks as 0 of 1 over square root of n. And this means that to cut the error in half, you need to quadruple your sample count to get one more decimal place of precision. You need 100 times more samples. That is why Monte Carlo is powerful for rough estimates, but not competitive with specialized methods for very high precision. So here's the implementation, and I want to show you 2 ways to think about it. So the naive approach would be a Python for loop. Generates one random point, check if it's inside, repeats n times. That works, but for n equals 1 million, it's slow. Okay, then we have the production approach that uses numpy vectorization. np.random.uniform with size n generates n random values at once, not in a Python loop. but in compiled C code underneath it is typically 100 to 1000 times faster. Okay, so we generate n x coordinates and n y coordinates in two lines, then the circle test x squared plus y squared less than or equal to 1. It's applied is applied elements wise across the entire array simultaneously. The result is a Boolean numpy array. Then we have inside.sum counts all the true values in one operation. Then we return 4 times inside sum divided by n. The second part of the code runs this at 5 different sample sizes and prints the estimates and error for each. When you run this, you will see the error systematically shrinking. Let me show you where this actually gets used. So for financial risk, value at risk, banks and hedge funds need to know what is the worst loss this portfolio could suffer over the next day with 99% probability. You cannot solve that analytically for a complex portfolio, so you simulate millions of market scenarios using Monte Carlo and read off the first percentile of the loss distribution. So another example, nuclear physics. The origin Stanislaw Ulam invented this in 1946 at Los Alamos, as specified in the beginning of the video, to simulate how neutrons travel through matter in a fission reaction. The equation had no closed form solution. Random sampling was the only way. Machine learning and the dropout estimation. Monte Carlo dropout runs neural networks inference multiple times with random neurons disabled each time. The variance across runs estimates how uncertain the model is about a given prediction. This is used in safety critical applications. Option price and Black-Scholes handles sample cases but breaks down for exotic derivatives. Monte Carlo simulates thousands of stock price paths and averages the payoff across all of them. We have the supply chain, simulates demand uncertainty, supplier lead time, and logistic disruptions across thousands of scenarios. Find the inventory policy that minimizes expected costs across all of them. And reinforcement learning, Monte Carlo tree search is the engine behind AlphaGo and AlphaZero. At each move, the algorithm simulates thousands of random game rollouts to estimate the value of each possible action. Complexity, again, two numbers. Time complexity is O of n linear. Each sample is evaluated independently, no dependencies. This makes Monte Carlo perfectly parallelizable. Run it into a GPU or across a cluster, and it scales linearly. Error conversions O of 1 over square root of n. To halve the error, you need 4 times the samples. For high precision work, more than 6 decimal places, consider quasi-random sequences like Sobol or Halton. They converge much faster than pure random sampling. 3 limits you need to know. First, slow conversions. O of 1 over root n is mathematically guaranteed but slow in practice. For a 6-digit accurate pi, you need tens of millions of samples. For financial VR at high confidence levels, the tail estimation requires enormous sample counts. Second, random seed management in production. Always set your random seed before running a simulation. Different seeds give different estimates. If you need reproducible results, and in production you always do, log this seed alongside every output. Third, variance is the enemy. A high variance in your sampling domain directly causes slow conversions. Variance reduction technique like importance sampling and anesthetic variate can often reduce the required sample count by 10 times or more, and this is deep topic worth studying if you use Monte Carlo seriously. So we have now 4 things that you know. 1. Monte Carlo uses random sampling to approximate answers to hard problems Sample evaluates, aggregates the law of large numbers, guarantees conversions. 2. Pi estimation throws n random darts into a unit square, counts how many land in the unscripted circle. Pi approximately equals 4 times inside over. Total more darts, more precision. 3. Error converges as 0 of 1 over square root of n. Each sample is independent, perfectly parallelizable. NumPy vectorization makes it production ready at millions of samples. 4. Used everywhere. Value risk in finance, option pricing, nuclear physics, Monte Carlo dropout in machine learning, supply chain, simulation, Monte Carlo tree. Search in AlphaGo. If this was useful, drop a like and tell me in the comments which applications surprise you most. Most people think this is just a math trick, but when you realize it's the algorithm inside AlphaGo and the risk engine of every major bank, it hits really differently. So in the next episode, we'll be talking about the knapsack problem, the classic optimization problem, how do you pack the most value into a bag with a weight limit. It sounds simple. The solution involves dynamic programming and it has direct application in cloud, cost optimization, and resource allocation in data engineering. So, see you there. By the way, if you are new to Python, I'm launching a Python formation. You can subscribe by filling the form in the description.